Alright guys, welcome back to Underground Science, and in this video, we'll be looking at the second phase of our cardiac cycle called the isovolumetric contraction. So from the previous video, we know that we experienced the A wave when our atria contracted the blood down to the ventricles, right? The A wave indicates the slight increase in pressure in our atria when our atria contracted the blood to our ventricles. Now, once we have our blood, we're going to go ahead and outline it again. So we had our 75 to 80% of our blood trickle down passively, right? So 75 to 80% of our blood came down to our ventricles from the atria passively as the atria were filling with deoxygenated blood and oxygenated blood, right? Compared to our right and left ventricles. So let's go and write that down here. So this is going to be indicating 75 to 80% of our oxygenated blood came down to our left ventricle passively. All right, so our atria didn't need to contract yet. Then we said that at the end of diastole, or at the end of ventricular diastole, our atria contracted. All right, and then it filled the rest of the blood. So then, when our atria contracted, we filled the rest of the 20 to 25% of the blood. And over here, let's go and write the same thing, 20 to 25% of the blood. All right, and when the atria contracted, we saw a slight rise in pressure, and this was called the A wave. Okay, now the isovolumetric phase, oh yeah, and also we said that while in ventricular diastole, the pressure of the ventricles was almost 0 millimeters of mercury, right? And so I don't know if I mentioned it in the previous video, but during ventricular diastole, our semilunar valves, so our pulmonic valve and our aortic valve are closed. All right, so both those valves are closed because don't forget that previously in our previous cardiac cycle, right? Because this is happening like every second, right? So one thing we should know is that, actually this is a good reminder, is that ventricular systole, so when the ventricles contract, it takes around 0.3 seconds for the ventricles to contract. And for ventricular diastole, sorry about that, when the ventricles are relaxing and filling with blood, so ventricular diastole, so when the ventricles are filling with blood, it takes around 0.5 seconds. All right, so 0.5 seconds. So in total, the time it takes for the ventricles to contract and relax is 0.8 seconds. All right, so the total is 0.8 seconds. So that's just a good thing to know. So we know systole is faster than diastole. All right, sorry about that. Okay, so now we see the A wave, right? Now in isovolumetric contraction, oh wait, we were talking about the valves, right? So the valves are closed because remember the previous cardiac cycle, our blood actually got pushed out of our pulmonary artery and our aorta, right? So we would want these valves to be closed so the blood doesn't flow back. Okay, now this is a new cardiac cycle. So ventricular diastole occurred. Now we're going to talk about isovolumetric contraction. So here what starts to happen is that now the ventricles start to contract, all right? Because remember in the beginning from our internal pacemaker video of the heart, right? So now we know that the AV node, right, the atrioventricular node, has received the signals, right, from the internodal pathways and the Bachmann's bundle, right, that initially started in the sinoatrial node, has received the signals and has started to transmit those signals down in order for the ventricles to contract. All right, guys, so let's actually, before we move on, let's actually label this well so everything makes sense. All right, so the right ventricle is also at 0 millimeters of mercury at this moment, right? Because we just finished the ventricular diastole phase, so it still hasn't started to contract yet. All right, but now we just said that the AV node is starting to send the signals and our ventricles are starting to contract, right? So now what's going to happen is that it turns out that in our aorta, the pressure in our aorta is around 80 millimeters of mercury. All right, and the pressure in our pulmonary artery is around 10 millimeters of mercury. All right, so 10 millimeters of mercury in our pulmonary artery and 80 millimeters of mercury in our aorta. All right, and so now what happens is when the ventricles start to contract especially our left ventricle, the pressures in our left ventricle will actually start to rise. So maybe it will start to rise to around 7 millimeters of mercury, right? 7 millimeters of mercury. As soon as it goes to 7 millimeters of mercury, the pressure of the left ventricle is actually greater than the left atrium. So what happens is that the mitral valve or the bicuspid valve will actually snap shut. Okay, so now it's not going to be open. With the help of the papillary muscles and the chordae tendineae, our mitral valve will snap shut because the pressure has now risen to 7 millimeters of mercury around, right? And that means that if the pressure is higher here than the left atrium, that means blood will tend to flow back, but we don't want that. So this closure of the mitral valve prevents that. Okay, so again, once the left ventricle starts to contract, starts to go up to around 7 millimeters of mercury, 7 millimeters of mercury in pressure, it actually goes higher. So 7 millimeters of mercury of pressure is higher than the pressure in the left atrium. That means blood will actually want to flow back to the left atrium from high to low pressures, but we don't want that. So that means the mitral valve will actually snap shut. Okay, so that's good. And the same thing happens in the right ventricle. So in the right ventricle, the pressure starts to rise also, all right? Because remember, both the ventricles contract at once. So it turns out like, let's say around, right? So the right ventricle's pressure will actually rise maybe to around 3 millimeters of mercury, all right? And as soon as it rises to 3 millimeters of mercury, 3 millimeters of mercury is actually going to be higher at a higher pressure than the right atrium. That means fluid or blood will want to flow back from high to low pressures and to the atrium. But then the tricuspid valve is like, no, right? Yeah, I'm not going to let that happen. And it actually snaps shut thanks to our papillary muscles and our chordae tendineae. Okay, and then from here, what happens is that from 7 millimeters of mercury, it can actually go up to around 70 millimeters of mercury. All right, so it can go up to around 70 millimeters of mercury, right? 70 to 75, I should say, right? Just to be in the range, right? So 70 to 75 millimeters of mercury in the left ventricle. Okay, and so now let's discuss if we're talking just about the left ventricle, now let's discuss the aortic valve. The aortic valve is still shut. Now, why is it still shut? Because the aorta pressure is 80 millimeters of mercury, which is higher than 70 to 75 millimeters of mercury, right? So the pressure will still, because of the pressure difference, the blood will want to flow back into the left ventricle. That's why the aortic valve still stays shut. So when we're going from 7 to 70 to 75, notice that in our left ventricle, the mitral valve is shut and the aortic valve is shut. And then for the right ventricle, what happens is that we go from 3 millimeters of mercury, right? And just to estimate what we could say, just to get the concept down right, is that because we see the left ventricle up to 70 to 75, we could say that the right ventricle, because we're indicating the ventricles are slowly contracting, right, and like kind of like slow motion, right, are starting to contract, we can say that the pressure in here can go up to maybe around 8 to 9 millimeters of mercury, right? But then if it goes to 8 to 9 millimeters of mercury, the pulmonic valve will still stay shut because the pressure in the pulmonary artery is 10 millimeters of mercury. 10 millimeters of mercury will be higher than 8 to 9 millimeters of mercury, so blood will still want to flow back, right, from high to low pressures. That's why the pulmonic valve will still stay shut. So we can see here that in isovolumetric contraction, there's no blood entering the ventricles or leaving the ventricles. All right, there's no blood leaving the ventricles because it can't, right? Because the semilunar valves are closed, and there's no blood entering the ventricles because these atrioventricular valves are closed and the semilunar valves again are closed. So this is why we say isovolumetric contraction, because even though the ventricles are starting to contract, the volume of blood is still staying the same in the ventricles. So it's called isovolumetric contraction, right, guys? And also, once our atrioventricular valve snaps shut, like we saw here, right? Once it snaps shut, that's our lub sound of our heartbeat sounds that we hear in a stethoscope, like the lub dub, lub dub, lub dub, right? So this is our lub sound. So when I believe we made a video for this, right? The heart sounds in the cardiovascular system playlist. But when the atrioventricular valves snap shut, right? When they snap shut, that is our lub sound. Lub sound. All right. So let's go ahead and finish that parentheses and go back. All right, so that's pretty much what happens during isovolumetric contraction. In the next phase, we'll see ventricular systole. All right, in this phase, the ventricles are beginning to contract, but in the next phase, we'll see full ventricular systole. All right, so when the blood rapidly gets ejected out, and then we see some more ejection of blood, and then after that, we'll see the fourth and final phase. All right, but anyway, another thing that we should know is before we end this video, remember the A wave was when the atria contracted in the ventricular diastole phase, right? But then when the ventricles start to rise in pressure and actually are higher than the pressures in the atria, we said the atrioventricular valve snaps shut. That snapping shut actually creates another slight rise in pressure in our left atrium. All right, if we take the example of left atrium, when the mitral valve snaps shut, it causes a slight rise in pressure, slight rapid rise in pressure. That slight rapid rise in pressure is called the C wave. All right, so there's a slight, sharp, rapid rise in pressure. All right, and that's called the C wave. All right, so that's good to know. And then, yeah, that's pretty much it. So if we want, we can do a slight review session real quick before we leave. So what happens is that the ventricles, right, slowly start to contract, and we said some example numbers here. It starts from 0, then it rises to 7. If we're just taking the left ventricle, it rises to 7. 7, as soon as it rises to 7, our mitral valve snaps shut because now the left ventricle's pressure is higher than the left atrium's pressure, right? So our mitral valve snaps shut. Then we said that it can rise up to around 70 to 75 millimeters of mercury, right? But it still doesn't open the aortic valve because 80 is higher than 70 to 75. So blood would still want to go down, high to low pressure, right? So aortic valve still stays shut. Then if we go over to the right ventricle, we have some example numbers here. As it goes from 0 to about 3 millimeters of mercury, right? Right when it goes there, we said, so right as soon as 3 millimeters of mercury is reached, we said that the tricuspid valve snaps shut, okay, because the second 3 millimeters of mercury is reached, the pressures in the right ventricle is greater than the pressure in the right atrium. So we don't want blood flowing from the right ventricle to the right atrium, all right? So again, these are just good example numbers, all right? So it's good to get the concept done by looking at how the pressures involved in the heart chambers cause the valves to snap shut, all right? So again, the tricuspid valve will snap shut, and then it can rise up to 8 to 9 millimeters of mercury, right? The pressure in the right ventricle, which is still not higher than 10. So that's why the pulmonic valve stays shut, because blood will still want to flow from high to low pressures, right? Because 10 is higher than 8 to 9 millimeters of mercury. And so, yeah, so in the isovolumetric contraction phase, there's no blood entering the ventricles and there's no blood leaving the ventricles. All right. And so that's pretty much it for the isovolumetric contraction phase. I hope to see you guys in my future videos, right? And in my next video of the heart, where we'll talk about the ventricular systole phase. All right. So the third phase of the cardiac cycle. I'll be talking about more cool topics, right, in the future about biochem, physics, and chem. Don't forget to hit that notification bell, like, and subscribe. See you guys later, and stay safe.